Today I'm going to talking about Matroid intercession, and I want to keep this like informal, so feel free to stop me anytime if you have questions. If I don't get something across, it's probably on me because I just got back and I'm still jet lagged actually, and so this. Today, so the paper itself, like there are like other results, but like today I only focus on one algorithm and the analysis of it. So I plan to give the full details. And towards the end, I'll say something about the other stuff in the paper. So how many people have seen matroids before here? Okay, everyone. Okay, so I'll just remind you the definitions like really quick. Oh, by the way, this is John work with Depala, Inter, Aaron, and Sahil. So let's start with matroids. So we are going to denote a matroid M. As you know, you have a ground set V. So we call V the ground set, and we denote the independent sets by I. So I independent sets. And so matroids, they satisfy two properties. So any subset of an independent set is also independent. So given an independent set, you actually get exponentially many subsets. And the other property allows you to make an independent set bigger. So you will have two independent sets, I1 and I2, so both of them are independent. So let's you move an element from the bigger one to the smaller one so that it's still independent. You have something in I1 but not in I2, so here I1 is the bigger one. And I2 with that new element is still independent. So that's matroid. And matroids are like combinatorial structures that generalize inner independence. So the name actually comes from matrices. So if you consider all the set of linearly independent vectors, that will give you a matroid. So that's called the linear matroid. And we also have the partition matroid as another example. So here the ground set would decompose into will partition into a bunch of subsets, and you have a capacity on each of the VIs. So let's call that S1 up to Sk. So these are integers bigger than 1, or 0. So here, any independent set will pick at most Si elements from Vi. So that will give you a matroid. So in general, matroids have many nice properties. You have these like things called matroid polytopes, and you know that the greedy algorithm will give you a maximum independent set. So today, the optimization problem that we are concerned with is the matroid intercession problem. It's one of the most basic polynomial time solvable combinatorial problems. So it's exactly what you expect. So here you have two matroids, M1 and M2, over the same ground set. And this is crucial that they're over the same ground set. And the problem is to find a largest common independent set. So some I that is independent for both M1 and M2.
So how are M1 and M2 given? Well, independence oracle or
Yes, good. I'm good.
Oh, okay.
I'm going to be talking about that in just a second. So that is the problem. It's polynomial time solvable, which was first proved by Edmonds. We don't need it today, but in case you're wondering why we have two but not more, so the problem is actually NP hard for more than two matroids. So we want to study the problem algorithmically, so we better have an access model to the matroid. Because like matroids in general, they don't have succinct representation complexity, so you need some way to interact with the matroid. And one of the most common model is the independence oracle. So it just tells you whether a given set is independent or not. And in the case of matroid intercession, you will have an independent oracle for each of M1 and M2. And we are going to denote the running time of this oracle by T. Any questions so far about the setup?
And the set V is known somehow?
Yeah, it's given.
V is given.
So what do we know about the problem so far? So here, I'm going to introduce a few notations. So we'll denote the size of the ground set by n, and we'll denote the value of the optimal solution by r. So this is equal to r. Oh, by the way, one example of matroid intercession would be the bipartite matching problem. So in that case, you have a partition matroid for the left vertices and another partition matroid for the right vertices. So, okay, back to the algorithms from before. So we'll denote the running time of the algorithm using n and r and t. So one of the nicest results in combinatorial optimization was by Edmonds, and he showed that this problem is solvable in polytime, which is essentially n_r squared. So in the original paper, people didn't bother with running time at the time, so he didn't state it, but if you analyze his algorithm, it will come out to be n_r squared. T is the running time of the oracle.
Oh, okay.
So you need like n_r squared oracle calls, and the running time overhead is also n_r squared, so that's kind of gets absorbed into n_r squared t. So subsequently, Cunningham gave a faster algorithm, and his algorithm once in time and out to 1.5t.
Are you combinatorial?
Yeah. So Edmond's algorithm, just a word or two about these two algorithms. So I'll probably talk more about them when I get into our algorithm. So Edmonds is like an analog to the shortest augmenting path algorithm for matching, for bipartite matching. And Cunningham is more like the Hopcroft-Cobb algorithm. So you do augmentation in batches. So that's also why it's faster by a factor of square root, which is exactly the case between the augmenting path algorithm and Hopcroft-Cobb. So, and there's another algorithm by Aaron and me from a few years ago. So it's not a straight improvement over the previous result, but in certain regime it's better. So it's kind of weird. So we actually have a overhead in the runtime encrypt, but we only need n square oracle complexity. So in the worst case, n can be as big as r. So if we take r to be n, it's solved better in that parameter regime, but it's not straightly better. So, and that poses the question, matrix intercession isn't exactly a very complicated problem, and normally you wouldn't expect, different competing optimal algorithm, like there should be one optimal algorithm. So that poses the question, like, can you, unify these things? Like, can you do something which is like strictly better than all of these? And that's what we did. So today I'll present an algorithm with this running time. So n out time, roughly. And it's also very similar to Edmonds and Cunningham. And basically, we only need like two very simple ideas over Edmonds. That's a good question. I wanted to work on it, but I haven't had the time. So far, the best lower bound for the best oracle complexity lower bound for the problem is due to McCarthy. So he had like a lower bound of like, I think 2n in his PhD thesis. So we don't even know if, we don't even know of a superlinear lower bound. And that is sort of surprising because like it's an information theoretic lower bound. So the proof is really just a random family of instances, and that's it. So that's going to be something that's probably going to be something obvious in hindsight, but difficult to come up with. Or maybe the problem is actually solvable in linear time. Who knows? Okay, so that's all the background that I'll talk about today. Any questions before I get into the technical stuff? Okay, cool. So let me first record the Edmonds algorithm, which is based on the augmenting path idea. So matroids, we don't have a graph, so I bet I have to introduce the notion of the graph and tell you what augmentation means in that case. Bless you. So this is the notion of exchange graph. So given a set which is independent for both, so it's a common independent set. We can define the exchange graph over S, G of S. So on the it's a bipartite directed graph. So on the left, we have S, and on the right, we have the elements not in S. So it's just V minus S. And we have sources and sinks. So
B minus S is independent sets that are not in the what is B minus S? It's independent sets that are
it's
in
the
one or
elements
the,
not in S.
oh, these are elements.
Yeah.
Okay, sorry.
So we also have the sources, and these are just the elements that you can add to your independent set and still make it independent. So, and intuitively, these are interesting because you want to make S bigger to solve the problem. So in the first step, you might want to find element you can add to it while maintaining independence for one matroid. So similarly, we have the symmetric notion for the other matroid, and we call it the sink. And in general, there are going to be more than one source and one sink. So these are the two sides. These are the vertices of the graph. And here are the edges. So edges go from between the two sides. It can go in either direction. So in particular, AB is going to be an odd of the graph if replacing A by B will still make it independent for one matroid, for matroid 1. And as you can expect, you'll go the other way if you maintain independence for matroid 2. So you go in the opposite direction, if it's the other way. So intuitively, like this is something that you expect to work. Like I discussed before, like given S, you want to make S bigger. So in the first step, you want to add something to S and still make it independent for matroid 1, I1. Well, you'll probably not be, you'll probably destroy the independence for I2. So you want to take out something, because like a subset of an independent set is still independent, so it's still independent for 1. But you take one element you remove one element in a way that is still independent from matroid 2, and you sort of keep doing this again and again, and you will get to a sink, you'll be independent. So here's the algorithm, which sort of formalizes what I just discussed.
That needs to be shortest, the shortest.
Yeah. Actually, it suffices that there's no shortcut.
No shortcut.
Yeah, but anyway, so here's the algorithm. You want to first, step 1, you construct your graph, G of S. Step 2, you find one shortest augmenting path. From a source to a sink. So any source to any sink. It doesn't have to be a specific one. If you would like, you can introduce a super source and super sink. But
So from the sources to S, you have this direction? You haven't said, you said the direction of edges from
it's just the same. B can be a source.
Yeah, but, so, I mean,
So
the edges
you-
you define correspond to swaps so far.
So these are the edges. So
But they correspond to swapping something from S and outside.
yeah.
But I think, don't you need some edges?
So you start with something you start with a source. So you can swap this B into S for some A and still make it independent for I2. So source is like for I1. So okay. And well, we call that the augmenting path for a reason. So we want to do augmentation. And that just means you want to remove all the AIs. And you want to add in all the BIs. So it's like replacing BIs by AIs by BIs. And finally, you just repeat until we are optimal. So that's the algorithm. That's what Edmonds proposed. Of course, this algorithm works because augmentation preserves independence. So this is the key property. Okay, so this is the algorithm, and we can analyze the running time of it. So step one would take, so in general, we have to check for independence between all the pairs of elements in S and V minus S. So we have n pairs of elements to check, and that once in time nRT. Step two is trivial because you know the graph and you can use any CS101 algorithm to find a shortest path. Step three is also trivial. It's just a linear time operation. And you have to do it at most R times. So that is going to be R iterations of the algorithm, and the total running time would be nr squared t.
Why does it need to be shortest?
So it's really in the proof. So you don't. So the short answer is that we don't actually need it to be the shortest. It actually suffices that there's no shortcut. So if it's shortest, there's no shortcut. And the fact that it doesn't have a shortcut will give you some structural handle into the extremes graph and can prove that you preserve independence. It's like a proof by induction mostly. Other questions?
Simple matroid, whether that is actually necessary?
Say it again, I'm sorry.
That you take an augmented path without shortcut. Because for matching, bipartite matching, it kind of magically, you don't need that property.
Mm-hmm. Yeah, there might be some intermediate generalization of matching, like some sort of special matroids that would allow you to exploit that, but I'm not sure if I know of something like that. Oh, by the way, so this is, just a remark, it's not really relevant to the talk, but even though this is a augmenting path algorithm, but if we translate everything back to, so for the special case of bipartite matching, if we translate everything back to matching, it wouldn't give you the normal augmenting path algorithm. So here, so for matchings, like the elements of V of your ground set would be the edges. So if you translate the language back to matching, like these vertices are actually edges of your graph. So it's a little bit different. but the inspiration was there. So this is Edmonds, and let me see how I want to do it. Okay. And our algorithm is essentially a fast implementation of Edmonds. And we only need two simple properties or ideas. So one property that will lead was actually due to Cunningham, like it's used in his algorithm. So let me see. So distances are actually monotone. So, well, first I have to tell you what are distances. So here I mean that the distance, so for any v, so for any element in your ground set, you can consider the distance from a source to S to V in G of S. So as you do more and more augmentations, this distance can only increase, like your level decrease. So we call this the monotonicity lemma. Again, it's also like the other property is not difficult to prove, is some induction matroid operations.
You mean from a fixed source or from the closest source?
From the set of source. And using this lemma, he was able to do like a Hofcroft style implementation of Edmonds, and obtained this speed up.
The algorithms are the same, but you can do it faster.
So at the high level, it's the same, but but he doesn't like reconstruct G of S every time. Like instead, it's just roughly speaking, is a partial reconstruction. So there's like some information you can retain, and which is still useful. And at the high level, we follow the same spirit. Other questions? Okay, so our algorithm. So our observation is that you don't actually need G of S. You only need the path. You only need like a shortest path. So if I give you a path, like you can easily verify that it's actually an augmenting path, right? And you can also easily verify that there's no shortcut. But so is it actually possible to find such a path without knowing G of S? So that's the sort of starting point of the algorithm. And more precisely, like you don't actually care about like one thing. You can consider the distance sets. So these are di, and this is just the set of vertices at distance I from the set of sources. So, if you know all the di's, you can find something in D0 and then D1 and so on, and that might save you time. So that was our starting point. But first of all, how can you actually construct all the DIs? Can you find them efficiently? Well, for starter, D0 is easy. So what is it? Anyone?
Sources?
Yeah, it's just the sources. And you can figure out the sources pretty easily. You just have to check it for each element for the definition. So, well, so it's not surprising that we want to do it solve inductively. So given all the previous DIs, can you find the next one? So given given up to DI, you want to find DI plus 1. And to do this, we will exploit two simple ideas. So one idea is based on potential function. So we'll do an amortized analysis. But I won't tell you what was the first idea yet, because it's going to be a trick question. Anyway, so our question is that given all the DIs, how do you find the next one? And intuitively, there are going to be two cases, right? Like depending on where the next DI plus 1 is, like it can be on the left or on the right, and that is sort of structurally different. So there we need to invent two different procedures to find that. So we have to do it from left to right and right to left, depending on where our next, depending on the parity of I. So your DI plus 1 can be here, or it might be on the other side. And that's going to be pretty different. So case 1, you want to do it from right to left. So in this case, our DI plus 1 is on the left. And so here's our DI, and we want to find the DI plus 1. So anyone want to try to do it? Well, for starter, we know DI plus 1 cannot be from, it cannot be from D1, it cannot be from D3, and so on. So we don't have to worry about any of this by definition. And this is what we want. Like we want to find something in A, which is not in any of these. So A is something not. And B in DI, so that S minus A plus B is still independent for matroid 2. So how can we do this fast? Well,
Is it S minus B plus A or S minus A plus B? I'm just confused.
Uh,
Because aren't you going to the left here? And
it's minus A.
Okay.
You want to remove A from, because like A is in S.
Okay.
So A is something here. So,
Draw all the guys in DI, and then you see which one can you add in.
yeah. So there's actually a so naively you have to check everything here, right? And everything can potentially be one pair. But so let's say, so we want to, we have B. Well, we want, like, eventually want to add B into it, right? So, and we know like A cannot be any of these, so like let's try considering this. Like if this guy is like not independent, then we know this B cannot be useful. So on the other hand, if this is still independent, then there's still hope. So we check if this is independent. If nope, then we know that wouldn't exist any A which makes it independent. Because like this set is going to be a subset of this guy. So let's call that S prime. Right?
So that set is at the level I?
Reset S.
Yeah,
S.
so sorry, so that, no, I guess
Why again? You want B plus D one of D minus one?
So we consider
Plus
this
you mean union, right?
sorry, it's the other way.
Yeah, but I'm saying this plus the union. So you want all of those D1 up to D minus one and
Sorry.
independent?
so,
Yeah. With this set.
so the DIs are, so you are assuming that they're independent out to distance I, di minus one, or you know that?
You know all the previous ones.
All the previous distance sets, and they're all independent of each other.
They're,
Like their union is independent
yep,
already.
yep.
Why?
Because like,
Why?
because like if it has odd parity, then it has to be on this side by definition.
I guess you say the union is subset of S. If that's
Yeah,
independent.
yeah.
That's what you say.
Yeah.
Okay.
So it's only like, it's not D1, D2, it's only D1, D3, and so on. But what's important is like you just forget all the elements, you know the distance of. Like these elements, like you know their distances and you don't have to worry about them. So here, like, this is sort of like a proxy to like what we want. Like if this set is not independent, then we know nothing is going to be independent because like any S minus A plus B is a superset of S prime. So by the first property, definition of matroid, you know this set cannot be an independent for any A. And if this is actually independent, then I claim that there actually exists such an A. Because like this is what we have, and by the second property of matroid, we can find elements here. We can find all but one element here, so that it's still independent. We can add all but one element here and still maintain independence. Sort of like reconstructing a base. But well, we still don't know the A, right? We know it exists, but algorithmically we have to find A. So how do we do that? It's like the first idea you see in CS. Say again.
Red for search or?
Oh. Yeah. So here, these are your candidates, right? So you can try to. So here, so far we know this is independent, and we want to add more to it. And we know like there exists such an A, so we can try to add half of this. So let's see, it's called. Yeah, it's getting a little bit messy notations. So let's call this, I don't know, S double prime. So let me find a better notation. Let's call this A, big A. We can partition A into two subsets, A1 and A2 of equal size, roughly equal size. And you can check independence of these two guys. If S prime with A1 is still independent, then you know such an A still exists in A2. And same for the other one. And you know one of these work because like A exists. So you just recurse, and we can figure out one A in not time. And once you find one A, you can keep doing it. Like, you can just move A into here, and you repeat the same thing, the same procedure on the rest of the elements. So the gist is that this algorithm is going to take you logarithmic time per vertex. Yes.
So you're going to take that either one of these unions is independent for some reason?
So if this is independent, then you want to recurse on. So if it's the first case, then you want to recurse on A2. So you partition A2 into two sets and recurse. And if not, then you want to recurse on A1.
So what are you maintaining at each point? So you've got this S prime and you've got A. What are the properties that we know of capital A? What are the properties we know?
So is this at the setup vertices with unknown distance? So is the vertices we haven't figured out the distance of.
And what is the relationship? They're in S?
So of S, because it's like on the left-hand side.
I see. So I see. So S, okay. So you've already know, I mean, I just want to make sure that one of the other of those cases, one of those two has to be independent. That's the question.
Yeah.
Why is that going to be the case?
Because, so we know that S prime is independent.
Yes.
And because both S and S prime are independent, we know that we can move like, so actually let me write this down to make this clear. So now we know both of these are independent. So we know that you can find something in S minus S prime. So that's going to be some E, so that S prime plus E is still independent. So that's from the definition.
Right, so you know there is at least one element
Yeah.
in that extra set, and probably just one, but yeah.
So, and once you find S prime plus E, you can keep doing that. So you can, you can find something in S minus, so let's call it E1, 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 E2.
So you got S prime plus E1 plus E2, etc.
And you can keep doing this until they are of equal size.
Okay, so, and the size of S prime plus A1, oh, I see, because S,
Yeah, they agree on all these elements. The only difference is that S prime has B, but S doesn't.
so there's really only one of those bad elements
Yeah.
in DI plus 1 that could possibly mess things up.
Yeah, and that's actually the element we want, and that's our A.
I see. So the point is, A can't be in both A1 and A2. So,
Yeah.
Okay, good.
So right to left, we know how to do it fast. So you see, I want to keep this. Is it okay if I write here?
You pull the right-hand board.
Okay. Just want to keep the definition. Okay, so now left to right. And so the two ideas are binary search, which we just discussed. And as I talked about before, the second idea we need is potential function. So it's an amortized analysis. And we use that to deal with the second case. So here now, di plus 1 is on the other side. So again, we have d1 up to di. So d1, d3 up to di. So given all the sets up to di, how do we find this? And of course, we have d0 here, d2, and so on to d minus 1. So for starter, again, well, nothing in di plus 1 can be from the previous one, right, by definition. So we don't have to worry about any of these. And we also don't have to worry about any of the previous. So these are the previous di plus 2, di plus 3, di plus 5, and so on. Because distances are monotone, so we can sort of introduce this notion of distance lower bound. So after we do an augmentation, the distances can change, but they can only increase. So we can use the old distances as a lower bound of the new distance. So these are initially the old distances. And so we know that if we want to find something in di plus 1, it cannot be from any of the previous ones. So that gives us a very level scope. So So the monotonicity lemma tells us that di plus 1 can only come from so this is the old ones. Right. So far so good. And we'll use the distance lower bound as the potential function. So this is our potential function. So now, again, we can sort of do the same thing. Like, so for every b, so we'll call this b. So for every b in small p in big B, we sort of do the same thing. You want to check if there exists some a in di, so that let's see, s minus a plus b is still independent. That's precisely what we want. Like we want to find something a here, so that a has an edge going to b. And it's basically the same idea as before. We know that to check this, it suffices to check it for this. If this guy is independent, then you know such an A exists. It's a if and only if. So again, it can be checked fast. But the problem is that like you may have to perform these checks many times, because like this B can be checked against di plus 1, it can be checked again against di plus 3, and so on. But the crucial observation is that because we use this as a potential function, because distances are monotone, it can be only checked out times across the entirety of the algorithm. So each B only check at most out times across all iterations. Okay, so these are all the pieces we need. So so the algorithm is as follows. So let me do it here. So the algorithm construct all the distances using these two sub-procedures. And once we have all the distances, you can actually find a shortest augmenting path easily just by backtracking in a DFS manner. So, and you just repeat. So the running time of the algorithm are limited by the time for finding DIs. Well, here, like for right to left is just logarithmic time per vertex. So the total time is only n naught r time per iteration. And we know that we have at most R iterations, right? Because like the final set has size R. So we only need R augmentations. So this is NR square, so NR log R. Sorry, T. So the running time for going from right to left is exactly what we want. And what about from left to right? So the bottleneck here is how many times you have to check for each B, and we know that you only have to do it for R times. We have R vertices, so the total amount of time we need for this is nRT. And this is across all the iterations. So that's it. I'm pretty sure some people have questions, so feel free to ask.
So this is, so you, by doing the distances first, you're sort of, I mean, the Edmonds cart batching kind of thing where you're getting a lot of paths at once, you don't get any savings because you're spending all your time constructing these distances? Is that the?
So we are saving time. So for case one, to go from right to left, so the case where di+1 is on the left, we don't really use information from before, from the previous iterations, like it's all flash. But here the key observation is really just binary search. And that's basically the missing piece from before. So for the other case, well, we used the monotonicity lemma by Cunningham, so it's sort of related, but not quite. Like his algorithm is like somewhat more complicated. So in fact, you can still do something like this. You can achieve a similar running time using Cunningham and binary search, but it's going to, oh yeah, I should have mentioned this. Sorry, I forgot about it. So if you use Cunningham and binary search, so just like what we discussed. You can get a running time of this, and this was actually an independent result by Gwen. So it's similar, but it's worse, but it's lower by a factor of log square. So that sort of tells you that it's something similar. By using the potential function argument, like it sort of gives you a more direct analysis.
So couldn't you do so don't you have this monotonicity of distances for the left side?
Yeah.
So why can't you do the same thing for the left side?
For this case?
Yeah.
You still have to spend log out time anyway, so.
Sure, but then you don't need binary search.
You still have to do binary search. Because like here, like the difference is that here, like we know, we start with, we start with B and we just want to check against B. That's all we need. Like we don't even need to know, let me see how I can explain this. Yep, here we actually want the A. Yeah, I can get into details, but bear with me because it's going to be a bit high level. So in principle, if you just want the distance set, you can actually do some saving. Here, I sort of cheated a little bit. Like I was like, you only have to check it against this set. But if you actually want to unravel the DIs to find a shortest augmenting path, you do need the A. If you want to solve go back. So here, actually in the second case, you also need to do the binary search thing to find some A. Yeah, but in any case, like you can try to like imitate what we did for the second case in the first case, but it's probably the limit anyway, because like it's like logarithmic time per vertex. So like we sort of like there's like, I mean, I don't want to be too bold in conjecturing this, but like, you know, this NR term actually comes from two different places. One being that you have our iterations, and each iteration is logarithmic time per vertex. Like here, it comes from another way. Like it's like our time, like the distance, the potential function is like the potential function analysis, like amortized analysis. So I don't want to be too bold, but it's tempting to conjecture that this is actually tight, like you sort of balance the two in some way. Okay, so I think I should stop. Like, let me just end by mentioning that, like in the paper, we also have like sort of a second part for solving the approximate version of matrix intercession. Okay, thank you.